And we're live. Hello, everybody. Welcome back to Networks and Cybersecurity. Today is Lab Day. We're going to be talking about DHCP, ICMP. We're going to be talking about those because we're done with the network layer. These are the last things we want to look at on the network layer. Let's see. I think we had a couple slides that we left off on too. So let me just pop those out real quick too. When we left off, we were at Traceroute. We were talking about Traceroute, which is what we're going to look at later in this lab with ICMP. We're going to look at Traceroute. Now this part will probably be homework. We probably won't get to it, just because it's a relatively long lab. And then we've got the IPv6 datagram. I just wanted to show you what the header looks like. You'll see that the fragmentation parts are gone, the options are gone. You have something called a flow label now instead, and you've got your source and destination are obviously much bigger. They while this says it's 32 bits, these are actually much larger. They would span multiple rows. They're much bigger. So since we ran out of IPv4 addresses, they decided, you know what, let's never run out again. And so there are probably enough IPv6 addresses to take humanity across the galaxy and still not run out. Alright, so 128 bits, really, how many is that? It's so many that addressing it becomes a pain. That's why we mostly work with IPv4. So typically you address it 8 parts, 4 hex digits long. So, oof, that's a headache, right? That's 16 bytes again. So that is a lot of addresses, enough for pretty much every planet in the galaxy to get an address or something in those lines. It's quite a bit. And then some of the other fields, just real quick, we've got version, which is pretty much the same, which is a 6 instead of 4. We've got traffic class, which was like our TOS field for quality of service and such in IPv6, only hopefully in IPv6 it will be used. In IPv4 we'll see it's quite seldom used. And usually it's just set to the same value. There are very few instances where it's actually utilized. Now we have a flow label field in IPv6 also specifically for high quality traffic flows like voice over IP, like voice calls, to allow them to be identified and grouped together quicker. So it's a little bit like fragmentation in the sense where you're reassembling a message, but it's more like to let you know this comes from this particular flow of traffic. It lets you know that very quickly in the header. And this is kind of a future use thing. I don't know if it's been implemented yet. There's still not that many IPv6 implementations out there. The adoption has been quite slow. And then you get your length field again, so the number of bytes in datagram. Notice you don't have to have header length anymore because you don't have options anymore. And now you get a next header instead of a type. They called it next header. You can still refer to it as type if you prefer. It's the same thing. It's telling you what the next layer up will be. And then, of course, we kept time to live because it's quite useful. Now it's been renamed to hop limit. So if you run into an IPv6 packet, that's going to be its anatomy. All right. Now back to the lab. Okay, so this time I'm going to go into the correct in-class channel. I'll try to remember to do that. All right. And let me know if there's any audio issues. Sometimes you get some weird audio distortion when I turn that device on and off. For this week's lab, you just have to open up the pre-provided trace. You don't have to generate your own. So just go ahead and find that DHCP session file that I gave you on Canvas, and as long as you installed Wireshark and said associate all trace files with Wireshark when you did so, which I'm sure everybody did. You can just double click on it, otherwise right click on it, open with, and find Wireshark. So right click, open with, and you would have to find Wireshark. All right. This opens up my trace that I recorded earlier. Why did I record a trace for this one instead of having you do it? Because in order to see the whole DHCP setup, you need to have connected to the network for the first time. You're going to be freshly connecting to the network, which requires you to disconnect, and we are on YouTube, so that wouldn't work very well, would it? But if you wanted to try it, and don't try it while you're trying to watch lecture, or you will go bye-bye for at least 20 seconds or so, 5, 10, 20 seconds. Depends how long it takes you to type renew. It would be ipconfig-release to give up your IP address and sign out effectively, and then ipconfig-renew to start the DHCP process again. So release and renew. We're doing other options with ipconfig, right? We're trying to copy what it shows us in ipconfig-all for the homework assignment, right? The one that was due tonight. And here's a different functionality of ipconfig. Okay, so let's get into it and try to see if I can make this more visible for everybody. Let's just do 2 full screen windows. And I'm going to need to make my font a little bigger in Wireshark, I guess. So let's go with gigantic. That should be good enough. Let me know if you can't see that. I will make it even bigger. Now we have here a couple of those not Ethernet type 2 frames. We have some of those 802.3 frames. This is a spanning tree 4 bridges frame. So this is something used by network devices to build some kind of spanning tree. Let's see, they have a different link layer payload. Very cool. Okay. First question on the lab asks you to sort by bootp or Arp. So let's do that. And we're going to look for the DHCP release message. So bootp, and then 2 vertical bars, and then Arp. And then again, don't forget to hit enter. You always got to hit enter to update your display. So we're looking for the release. That's the very first one. Awesome. Okay, what are we supposed to do with it? You can take a snip or something to show you found it. What is the source and the destination address? Okay, that's a pretty easy one. Let's see where we can find that. Source and the destination address of the release. So we're on the network layer, so if I just say source and destination, I'm talking about the network layer, the IP address. All right, so right there, Internet Protocol version 4. It's one of the things that's in the top level summary. The source is 192.168.164. Remember, again, that's that reserved address for local area network use. So 1.64 there, and then the destination is 254. So when we were talking about where the router's at, we were usually talking about it being at .0 or .1. This guy's at 254, so you see it can be not at .0 or .1. It could actually be anywhere in the whole range, and in this particular case, it's at 254. So a DHCP server, the destination is 254. You can also open the dropdown and find that stuff in the actual header. Remember, that's at the end of the header. And let's take this opportunity to point out that if you click on the Ethernet frames header, it's going to highlight it in blue down there, right? You're going to see that the first so many bytes are the Ethernet frame header. And you see all that different stuff that you were expecting that we learned about last time. You got your destination as the first 6 bytes, then source is the next 6 bytes, then type is the next 6 bytes. And then once you get into the next layer, you're immediately looking at the next so many bytes, right? So we are looking at a continuous stream of bytes whenever we talk about a packet. All those headers and stuff are abstractions we use to make it easier for us to think about. We're looking at the header being just bytes after the first header. Okay, so we've got the source and the destination at the end of that header there. And so you can see what the IP address looks like in hex as well, that it's pairs, four hex pairs, if you wanted to do it in hex instead. What's our next question? Can you determine the IP of my DHCP server? Well, yes, it's the destination there, right? It's wherever you're sending that release message to, that's got to be the IP of the DHCP server. So it's 192.168.1.254. So the release is 64 saying that they are giving up their stake to 64 early, and they're telling 254 you can reuse this IP somewhere else. I'm giving it up. So if there's another machine that comes along that needs an IP, then it can give it to them. So take away the filter, and then notice that the background traffic from different applications starts getting lost between 6 to 11 seconds because you're no longer connected to the internet after you yank out that IP. It's the same thing as yanking out your Ethernet cable or turning off your Wi-Fi. You're just not connected anymore. No one can reach you. You can't reach them. In particular, look at DNS messages, which we'll go over later. Your computer is showing IP associated with different services like Steam, Discord, etc., and then getting back unreachable replies. So I did this while I had all my browser and Discord and Steam and all these different applications open. So let's see what happens when you lose the internet. Now remember, you got the timestamp on the side here. So you got the timestamp on the side here. So it started with 10, 20, 30, 40, or sorry, these are 0, 0, 0, 1, 1, 2, 2. That's seconds that have elapsed since the start of the trace. Okay, so let's look for around the 6-second mark here. So I think it starts somewhere around here. We start to get, there's a destination unreachable, no route to destination. It's one of those ICMP responses we were talking about. And then we get some others here as well. There's a retransmission, which we'll talk about later. There's another destination unreachable. Here are DNS queries going out for, this looks like something Microsoft. There's one for Steam. Both of those come out as unreachable. And another for Microsoft, another for Steam. Those come out as unreachable. So at this point, I have lost the internet, and all that stuff is inaccessible. There's Discord, also unreachable. So all that stuff stops being accessible to me because I don't have an IP address. Now find the DHCP discovery message. So we're going to have to sort by boot P again. Who is this addressed to on the network layer? And who is it addressed to on the link layer? Alright, so I'll wait for this one in chat. Find that DHCP discovery message and tell me in either chat who it is addressed to at the link layer. Who does the discovery message go to at the link layer? Somebody said broadcast, and that is correct. We see it's going to all Fs. It's going to broadcast on the link layer. You see that in the summary there, or you can expand it and see it here in the destination as well. The destination is broadcast. So when you connect To the network, you want to broadcast out your discovery message. You use the broadcast IP address on the network layer as well. All right, so you're using the broadcast IP address on the network layer, all 255s, and you're also using the broadcast address at the link layer to facilitate that because the network layer has no true broadcast functionality. It piggybacks on the link layers. So the destination is all 255s on the network layer and all Fs on the broadcast layer. That is to say that it's all ones on both, right? Because both 255 and FF are just representations of all ones. In fact, if you click on the 255 and look at its hex value, right, it's also going to be FF, 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 FF. It's 4 sets of Fs, just like the MAC, right? And that's, I'm looking down here in the packet details, right? The highlighted part, when I click on destination, is all Fs. Okay, what's the transaction ID, and is it different from the releases? Transaction ID is also in that summary, and yes, it is different from the release. You can also find it in the details of the DHCP Discover. It's going to be right there, transaction ID. And you'll notice that it's also represented as hex because it matches the bytes that you see down here, right? So if you click it, you see it's 88, 71, A8, AF. That is the same as you see in the 4-byte raw stream. So that's a transaction ID for you. And it's different from the release because this is a different transaction. The release was a whole separate command in a command prompt, right? So it's a totally different transaction. Am I requesting a particular address? And if so, how is this possible, given that I just gave my address away? So am I requesting a particular address? How would I tell? Where should I look to see if I'm discovering a particular address? So tell me what it is and how you found it. Where's the address I'm requesting? Notice we're kind of skipping over this user datagram protocol that's sandwiched between the two things we've talked about because we haven't talked about UDP yet. That'll be our next up. So none of the info is going to be there. I'll tell you that. The port information, which we talked about a little bit, is there. And that'll help you if you want to sort. You could sort by 68 or 67, but otherwise the info is going to be largely in the 3 sections we've already talked about. The DHCP payload, the datagram, and the frame information. So how did we find what address we are asking for? What's the rest of the question? Are we requesting a particular address? How is it possible that we just released it? Where would we look for that? Someone posted the MAC address, and that is the link layer address, but that's not what we are requesting on the network layer. We're using DHCP to set up our network layer address. So how do we find what network address we're asking for? Someone said option 50, requested address under the DHCP protocol. So there are quite a bit. I told you the header was quite long, and there is indeed down here in the options a option for requested IP address. So one of the things you're getting on the homework is the IPv4 address. So that would be something that you would need in order to deliver DHCP later. Your application would need to save this. So your operating system obviously somewhere hangs on to the old IP address that it had, and the next time it connects via DHCP to your internet, to the same network, it'll ask for it back because it's easier for all parties involved if you just stay at the same place, right? So it's just traditionally a little easier for maintaining your network if you don't get a new IP every time. So most machines will remember where they were at. They will ask for it again. And most DHCP servers will not hand out recently used IP addresses to new machines, to other machines, until they've exhausted their supply of others. Okay, so they'll keep 6.4, this DHCP server will keep 6.4 kind of reserved for me for a bit, unless it's out of IP addresses other than 6.4, then it will start to give out those ones that others have used in the past. You also see host name in the options, another thing that you have to retrieve in the homework. You can see mine in the packet details was Commander Fish. All my computers are in the Fish family. Okay, so it was here in the packet details, and the reason that we were able to see it is because the operating system held onto it, saved it, and requested it again on its reconnection. So it's not like we still had it or anything, it's just something that somehow the operating system saves and asks for again the next time you reconnect. Now we need to sort by bootp or ARP. Bootp or ARP. We see a bunch of ARP messages, all sandwiched between our DHCPs, which is no coincidence. So, what does the DHCP server do immediately after the discovery request for about a second? And why does it do this? So, of course, I'm talking about the ARP traffic here. What happens immediately after the discovery request? It sends out a bunch of requests. You could call these probes too, but I think these are just labeled as requests because of how my router structured them. They didn't get identified as probes by Wireshark. So we've got probes for basically everything from, it looks like 64 up through 84, it looks like. It looks like it probed about 20 IP addresses, and it wanted a response to itself, so back to the router. So it sent out requests for about 20 IP addresses. Why would it do that? Why did the router, the DHCP server, send out a bunch of ARPs? I like to get rid of the number column. It's not very useful unless you're talking to somebody and you're trying to point to them where you're in the trace. You want them to look. The DHCP server, someone answered, the DHCP server tries to find out whether any of the probed IP addresses are already taken. Yep, so it is looking to see if anybody thinks they have one of these IPs already. If so, let me know. That is it preparing to make an offer. It's going to make an offer on one of these. Why would you send out so many? Well, they're fairly low overhead, and on a congested network where it's almost full, if 19 out of 20 are taken and you have to send out another round of probes, that would make the whole DHCP process take longer. So at this point, it's trying to just find one that it can give you. It's actually going to probably give me the one I asked for, which it asked for second. It asked for 7.1 first and then 6.4 right after. But it's trying to find at least one available address in this range that it can offer me. So it's going to offer me one of these, and it sends out so many to make sure that at least one of these is going to come back offerable. And you'll see, by the way, it says for about 1 second, so check the first timestamp after the discovery. So it takes about, the discovery comes in at about 11.5 seconds. The first ARP gets sent out at about 11.8 or so, 11.9. So about 0.3 seconds to send out the first ARP. And they're all pretty much sent out over the course of 0.2 seconds. The last one comes out at 0.89. So how long is it appropriate to wait for an ARP reply before you just assume that that address is not taken? So how long does the DHCP server wait before it confirms that that address is not taken and sends out the offer? Should it wait a second, 2 seconds, 3 seconds, 4 seconds? In this case, how long does it wait? About before it decides that the IP it was going to offer me is good to go, that no one's sitting on it right now. How long did it wait before sending an offer? Someone said it waits about 1.05 seconds. Let's see, 11.89 to 12.55. A little bit under 1 second. Looks like about half a second that it waits. Yeah, so ARP replies are expected rather quickly, right? If this was as one of these were actually online, in particular the one that it's going to offer me, if this were actually online, it would have about half a second to respond to stake its claim before its IP address got offered away here. I'm not actually sure what happens if you don't respond to one of these ARPs and your device actually was connected. It's a very difficult thing to set up. I don't know what happens in that situation. If the router mistakenly decided that you were offline because you responded too slowly and gave your IP address to somebody else, not sure what happens in that scenario. So something you might want to look into. Pretty cool situation. Also, another way that you can mess with somebody's network, right? Let's bring a little cybersecurity into it. How can you make it so that nobody can DHCP connect to a network? What's a really simple trick to ruin all DHCP requests, basically, without even having to mess with the DHCP process itself? This goes back to sending out fake ARPs, right? ARP spoofing. What can you do to block everybody's access to DHCP via ARP? Yeah, a couple answers. Basically, spoof all of these responses. Just respond to all of these and pretend that you have them. You can make up a fake MAC for all of them too with MAC spoofing, and just pretend that all of these are occupied. Then the DHCP server will have nothing to give out. So you can squat on basically every IP address in the network, so the DHCP server has nothing to give out. That's a pretty trivial attack to implement, pretty hard to fight back against. So local access, being able to plug directly into the LAN, is a pretty nasty level of access. You can do quite a bit of terrible things at that point to grief people's networks at the very least. So companies should take the ability to get local access pretty seriously, and they usually do. There's usually, for everybody that doesn't work there, some kind of guest network, and if you're really security conscious, all the Ethernet ports should be kind of hard to come by. This is where IP really shines, is that nobody can just take an Ethernet cable out of one machine and put it into their nefarious machine. You know, you've got to connect to the Wi-Fi or find the router or whatever physical device it is and try to get a cable into it. So it's nice to not have your Ethernet cables exposed from a security standpoint, but from every other standpoint, obviously Wi-Fi is a worse connection, so most places are not going to opt for that. They're going to actually run their Ethernet cables. As well they should. It's definitely not worth the security advantage. Okay, so any relationship between what the DHCP server is doing and the address that was requested. So we already saw that one of the requests was for that address, and the others are for addresses around that number too. It went 64, I think, and then the 20 IP addresses above it. So it used that request and which addresses it was going to check. Now we're going to find the DHCP offer, and what is the source and destination of this one? Let's have a look. The offer. So remember, the offer comes from the DHCP server to the client. So let's check out what the source and destination there are. This is coming from the server to the client, and the source is the DHCP server's IP, the router's IP, but the destination is still broadcast because our device that is doing the DHCP discovery does not yet have an IP address. But I did talk about this when we were doing the slides. What would it be on the link layer? Because when you send the discovery message, your source right here is your address on the link layer. And so when the server responds, it could have responded back to that MAC directly, but instead it is by convention broadcasted. The offer is also broadcasted, sent to the broadcast MAC instead of to the MAC address of the sender from the discovery. Okay, it's broadcasted. And because we do that, right, because we send it out like that instead of sending it out to the destination directly, that's one of the reasons that we have the transaction ID, so that if there are multiple DHCP requests going at the same time, those are all being broadcast. So there might be multiple offers floating out, all on broadcast, right? You only look at the one that matches the transaction ID of your discovery message. Okay, so it's because we send all the offers out on broadcast. That's one of the main reasons that we have a transaction ID. So what is the source and destination address of the offer? The source was the DHCP server's IP, that 254 IP, and the destination was still broadcast. What is the DHCP server's MAC address? So we can see that now because they've responded. It's the MAC address in the sender field. You can look at it there as well. Source, it's the MAC address in the sender field of the offer. How long is your lease? Where would you find that info? Where do you find how long is your lease and when can you try to renew it? How long is your lease and how long is your renewal time? Where would you look for that? We can do the next question at the same time too, actually. It's in a similar place. What is the router's address on this network and the subnet mask of this network? And I'll leave converting it to slash notation to you because I don't know how to do it. I just consult the table. And I think you should too, because not a skill worth learning, in my opinion. You can always consult the table. Someone said options 51 and 58, so let's have a look at what those are. It's going to be at the bottom. 51 is, that's 3. 51 IP address renewal time. Let's see how long it is here. 1 day, 86,400 seconds. Okay, so how many bytes are reserved for this option? You've got 1, 2, 3, 4, 5, 6 bytes. 6 bytes. So what's the largest number? Is it 6 bytes? Yes, but one of them's a length field. So we're actually looking in terms of the time. Oh, you can just alter the length field. So if you want to do longer than that, you would just send a longer length field. But 86,400 seconds cleanly fits into 4 bytes. And normally you wouldn't do longer than a day or so, maybe a couple days. In that other option, the renewal time, I can ask for a renewal after 12 hours, so significantly before the expiration time, half. So I can ask to renew this IP for an additional day after just 12 hours. It's not necessarily a day. The sysadmin can configure how long the lease times and renewal times are. They might have changed them in that interval, but generally you're not going to change them once your network's up and running, so it would probably be for another day. And then someone said the router and the subnet mask are also options. So we see option 3, the router's address, 192.168.1.254, which happens to be the address of the DHCP server as well, because this is a home network and it has the router doing everything, being the DHCP server and the router and all the other hats that it wears. If this was let's say we did this at John Carroll, for example, you would have a different address for the router and the DHCP server because they have a dedicated DHCP server. And you got your subnet mask right there. That should be one of the ones that you remember, by the way, just offhand. So you should remember the most common subnets, the ones that are used for let's say your LANs and stuff like that. So the 10.0.0.0.01 and the 192.168.0.01, those both have very common subnet masks. This and the one for the 10 series, those are the two that I think everybody should remember. So remember what this one is, right? Okay. In slash notation, obviously, once you look it up in the table. You can put the answer in chat once you've looked up what it is in slash notation too, if you want. What is the router's IP and the subnet mask in slash notation? Router's IP and subnet mask in slash notation. And the answer to all those questions were the different options where we found them and the times. Somebody posted already, /24, yep, so remember that's the /24. And somebody posted it with the router's IP before it. That'd probably be the best way to type it out, the router's IP and then /24. Find the DHCP request. Remember the request comes after the offer. Weird. That's the way it is. Find the DHCP request. Is this message broadcast or sent to the DHCP server only? Let's think about that. So why might it have to be broadcast, or why could it be sent to the DHCP server only? So this is coming from the original discoverer, the machine that wants a new IP, back to the server. The server's IP is already known to it. It just sent it here. It knows the MAC as well. So we'll see what happens on the link layer too. Is this message broadcast or sent directly? I'm going to get rid of my ARPs here too for cleanliness. Okay, so here is my request. And let's look. It is sent to broadcast still. And also on the link layer, sent to broadcast still. So why is that? Again, I know the MAC address of the DHCP server at this point. It was in this message as the sender. Okay. But instead of sending it to them, I send it to broadcast. And again, this is where that transaction ID comes into play. The DHCP server might be receiving multiple requests at once, so it's going to filter out which request belongs to who by the transaction ID. So the discover message builds that transaction ID, and then it's used for the rest of the transaction to track what's going where. So why send it out to broadcast again? Well, because you still technically don't have an IP address, all right? And so you shouldn't be talking over the network layer. You properly wouldn't be able to fill out the IPv4 field because you don't yet have a source address, right? So you wouldn't be able to fully fill out this header because you do not yet have a source. You have not yet gotten that IP address. Although this is your message to request it, you don't officially have it until the acknowledgement or until this message is received. Okay, so you send it to broadcast still. What's my computer's host name on this network? This typically generated your computer's name in Windows and is used to configure some router settings. We're going to look at that in the options again. We already looked at that though, as the host name here. Mine is Commander Fish. So this is usually generated using the username or whatever it is that you typed when you first set up Windows. You set up whose computer is this or whatever. It asks you to name the machine. It's going to use that as your host name on Windows. I don't know what it does on Mac. Somebody with a Mac can tell me what it picks for your host name. Most versions of Linux, same thing. It uses your user login. All right, so that's that question. Great. You can just do snips of these or however is easiest for you to answer these questions, by the way. I'm not terribly picky. Snip is probably the easiest way. Just if you're on Windows 10, Windows key, Shift S, highlight the part you want to take a screenshot of, and then paste it. So Windows, Shift S takes a quick snip of the part of the screen you want addressed, and then you can turn it in. So something like you might just do here. If you were a little bit of an overachiever, you might do the whole thing, point out that it's down there too. Something like that. Find where it says that this is a MSF, Microsoft 5.0 device. That means that this is a Microsoft Windows system running Windows 2000 or newer. Options that follow are unique to the vendor operating system. So let's see. MSF 5.0, and we're looking for this in the request. Where are these? MSF options. Are they in end? Are they in vendor? Look at that. Vendor class, MSF 5.0. And then where do we see those extras? I got, someone said vendor class identifier. Yep, that's where MSF 5.0 is at. And then we're looking at parameter list for the other stuff. So this is some stuff that's specific to Windows, for example, NetBIOS and other cool stuff like that. And then also Windows, being a little odd, asks for the router again, asks for domain name, asks for subnet mask again. So these are coming from the operating system, and they're asking for certain features. Some of these might be unique to the operating system. Something like NetBIOS, you're probably not going to have that on Linux. And others are just things that Windows wants for whatever reason. So let's see if these get transmitted in the next message. Let's see if those options get sent out again. Find the DHCP ACK. Now, is this broadcast or sent only to the client? So let's think. So we sent the request. We were already offered the IP. We sent the request to confirm that we want it. At this point, we should be good to go. At this point, we have an IP address. But the DHCP server has not yet acknowledged that we are good to go. So perhaps we will send it to broadcast again. Let's see. So the ACK goes out to broadcast again. Right? So you are still not completely good to go and set up on your IP until you get the ACK. So once this message arrives, then you can start talking over not broadcast. Okay, and again, it's still broadcast at the link layer 2. Goes to all Fs there as well. This one has a source, of course, because this comes from the DHCP server. That one does have an IP address of its own. But this goes out to broadcast again, and this is the last message that will go out to broadcast in this transaction. From this point onwards, you'll be able to communicate using your IP. So let's look. This happens at 12.57 seconds right here. There's the DHCP acknowledgement, and then there's some IPv6 chatter here. We see these super long addresses, and then right there we see the first address where my machine sends out using .64 as its source and something else as its destination. So it starts communicating over .64 right away after that DHCP acknowledgement. It's able to start communicating over its .64 address. So as soon as it receives that ACK, it can start using its newly established IP address. So if we look back here for some other ones, we'll see that it's not able to use that .64. There's some mostly IPv6 addresses here. But yeah, the only one you see before that is the release. So it's not able to use that address until it's fully set up at the end of DHCP. So let me sort that again. Do transaction IDs match for all the communication from the discovery through now? We can see very easily that they do. So the discovery message has that 8871A8, and we can see in the summary up there that they do. And we can also see that in the DHCP options and settings here. Let's see, where's that transaction ID? Right up there. And we can see that that matches for all of these. All the way down. Sort by bootp or ARP again. What does your computer do once an IP address has been assigned to it? And we'll see three things here, repeated several times in some cases. We got to explain the significance of these actions and why we might have wanted to repeat them. All right, bootp or ARP. All right, so we're looking at the stuff that happens after the ACK. There are two ACKs here, so be careful you find the right one. We're looking for the ACK for the request. We haven't gotten to the inform yet, so the ACK that happens at 12.57 seconds. Okay, so there's a bunch of messages here. Broadcast for who has 254. Okay, we get an answer. Who has 254? We get another answer. The same one, obviously. Okay. Who has my own address? Who has .64? That's a probe. Obviously nobody answers. Or we could answer ourselves, but that'd be strange. So we just don't. Ignore ARP messages from yourself, about yourself. Okay. And then again we ask for who has 254. Again, we get the same answer. And then we start asking for some others, 167.64, 167. And then one more time, who has 254? Same answer. Who has 254? Same answer. Who has 64? Ourselves, our own. No response. Except we get this one. What's that? Where does it come from? Well, okay, first of all, let's look at our source MAC address when we send this one out. We're D4, 3D, 7E, 4C, 80, 32. Okay, and then we respond. D4, 3D, 7E, 4C, 80, 32. Okay, so somebody gives us a request. We send a reply. Honky-dory. Another one, we send an announcement. So we update an announcement right after. And then a couple repeats again. Who has 254? Who has 254? Again. So why do we keep asking who has the router's address? We did it like 7 times. Who has the router's address? And then we also sent out who has our own a couple times there. So we sent out probes for ourselves. And also for this 167 address, sent out a couple for the 167 address. Why'd we do that? So the router one, obviously we want to make sure that the router is where it is. So we just kind of confirm, figure out where it's at. You'll also notice that in the offer, where it told us the router's address, it told us the router's network level address. It did not tell us the router's MAC. Okay, so even though we could have interpreted that from the fact that the router is the DHCP server and we have the sender's MAC right there, we actually don't do that kind of guesswork with DHCP. We get the IP address of the router, and now it's on us to determine its MAC using a link layer protocol. Again, we want to try to encapsulate everything. So if we want its MAC, we have to send out an ARP, as is tradition, in order to get the MAC of the router. Now, why do we do it several times? I don't know. It's just something that is done just to make extra sure that you've gotten it correct. Or it's possible that other programs, maybe Windows or other applications, needed to know the router's address as well, the router's MAC as well. Every time something needed the MAC, we might have just sent out a new ARP query just to be sure. So this is something that's decided at an implementation level. And then we also, somebody said in chat, sent out an ARP announcement, right? So as soon as we were established in this network, we waited about 3.5 seconds after getting our IP established to send out an ARP announcement. Before we sent out the announcement, though, somewhere in here we sent a probe for ourselves, just to make extra sure that nobody is parked on the same spot as us. Nobody thought that they had this IP. There's not a conflicting device that also thinks that it has this IP. So we sent out a probe to make sure. Once we didn't get a response back for a bit, then we were able to confirm that we have this one for sure, and we sent out an announcement. Okay, and there's also some requests for 167. Those are probably just legitimate probes for some relationship that we have with 167, whatever it may happen to be. And that's going to be it for today. So the rest of it is homework. We've got this ICMP part at the bottom. You can easily do either on the CSVMs or on your own machine. There's no risk of disconnection or anything, and the commands are pretty simple. It's designed for Windows, Mac people. You can look up your commands. They're pretty similar. All right. Yeah, that's it. Thanks for tuning in. And okay, I'll see you guys on Friday. Lab is due Friday evening, and homework is due tonight. Adios.